We're going to look at two examples of how composition of functions can be used to write new functions from a verbal model. In our first example, a meteorologist is inflating a spherical balloon with a helium gas. The radius of the balloon is changing at a rate of 1.5 centimeters per second, and our task is to express the volume of the balloon as a function of time. So when I read this, I start to focus on volume as a function of time, knowing that at the end I'm going to have a function that reads v of t. Now, where am I going to step off on this? Well, I know that the volume formula for a sphere is 4/3 pi r cubed. And if I write it as an equation, that's what it is. But that's really a v of r function. That's volume as a function of radius, saying if I know the radius, I can calculate the volume. And that's kind of the sticking point right here, that radius, that I need to have time in there instead of radius. And so what I would do is I'd write a second equation, realizing that how the radius of the balloon is changing in terms of time. So I'd have an r equals 3/2 t, the fact that the radius of the balloon is increasing at 1.5 seconds per 1.5 centimeters per second. Once again, I wrote this as an equation. If I put this in function notation, I would have 3/2 t being equal to r of t. With those two ideas, I can make a substitution, create a new function, v of r of t, meaning I'm going to put the function r of t into the function v. So that would be 4/3 pi, and I'm going to replace r with 3/2 t because they are equal, and then I'm going to need to cube that. From here, it's a matter of some algebra, 4/3 pi times 27/8 t, and I can do a little reducing here. The 4 reduces with the 8, I get a 2. And the 3 reduces with the 27, and I get a 9. And my final function will be v of t equals 9/2 pi t cubed. Oops, I missed putting the cube in that line there. So 9/2 t cubed. And in previous classes, you may have called this the substitution method, because that's really what I did. But now formally we can see it as a composition. Why would you bother doing something like this? For ease of calculations or for efficiency of calculations. If we did not compose the functions, we would have to get our answers, if somebody was interested in this, we would have to work through these calculations in the function r of t to get a radius, then take that answer, put it into that, and then run through all of these calculations to get our final answer. But when I put the two functions together and simplify, I get a single function with fewer operations than the two operations individually, and that can be just a matter of efficiency. So there's one example of that. Our second example here, the diagonal, which we're going to call d of a cube, is the distance between two opposite vertices. We're going to express d as a function of the length of the edge cube. Now, this is a case where obviously a diagram would be very helpful and a good place to start. So I'm going to draw the best cube that I can seem to draw. And we're going along pretty good here. And what we're going to have for a diagonal is maybe I should put in some so that we can see through the cube. And the diagonal is going to be the distance from opposite vertices. I'm going to choose two opposite vertices. I'm going to take the top front and the lower back. And that distance d slices through the middle of the diagonal. And I've been told that the edge of the cube is x. So I want to find out what the length of the diagonal is in terms of x. And the way I look at it is I can build some right triangles here. I can drop a vertical here, and then across the base of that, and I have a right triangle, the hypotenuse of D, one leg of X, and I've got another leg that I just don't know. So for the time being, I'm going to call that Y. I'm going to call that Y. And I could write, by using the Pythagorean theorem, that D squared equals X squared plus Y squared. And so that D equals the square root of X squared plus Y squared. Now remember, in this case, I cannot simplify the square root of X squared plus Y squared. I can't take the square root of a sum or a difference. And I've got a function D. I'm expressing D as a function of, except right now I have a D as a function of X and Y instead of just X. So I need to be able to get rid of the Y somehow. This is where, once again, a secondary equation and use of composition of functions will come into play. What I can do is I can build a second right triangle there, which has legs of X and a hypotenuse of Y. And that means Y squared will equal X squared plus X squared. So Y squared will equal 2X squared, so that Y is equal to the square root of 2X squared, which will give us Y equals X times the square root of 2. And that's exactly what we want. Now, if we go to function notation, I erase this Y, I can call this Y of X. Just like up here, I could call this D of, well, X comma Y, so it's a little weird. But I can make that substitution. So now my D would be equal to the square root of X squared plus X times the square root of 2 squared. X root 2 is equal to Y, and I had a Y squared there. D equals the square root of X squared plus 2X squared. Within the parentheses, the X squared is X squared, and root 2 squared is going to be 2. So that D equals 3X squared. Take the square root. Simplify it down, put it in function notation. D of X equals X root 3. And I've accomplished the task of expressing the diagonal through the middle of the cube as a function of the length of the edge. So it's X root 3. And so just an idea of looking at that idea of substitution method through compositions and being able to write a function from a verbal model.